Yeah, thank you for the kind introduction. And also welcome from my co-speakers, Scott and Moritz. So today we are addressing an important question that many modern companies are facing. How can we bring together large collections of data with privacy regulations such as GDPR? A teaser for the talk can already be seen on this slide. We are looking at images with personal identifiable information. So here we can see an image of a front video camera. We can see a license plate. We can see a person looking into the camera. So we're dealing with privacy relevant data. We're splitting it up into two parts, kind of. So we have one part that contains all the privacy parts. We have another part that contains pretty much the background. And then at the end, we want to train a neural network securely. In order to make this kind of vision into reality, we had to deal with a pretty large stack of technologies. And therefore, we as Bosch teamed up with Intel and Edgeless to make this vision into a reality. But first things first, let's talk a little bit about why we are even here. So usually when we talk about data, we see this as kind of the new oil. So meaning the more data a company has, the more valuable it is. So the more use cases you can realize, the better your models become, and so on and so forth. So in short, it can be extremely well monetized. But in recent years, we have also seen increasingly that it can actually be pretty dangerous. So Bruce Schneier phrased here this very well, and he said, data is a toxic asset. Or in other words, if you have a lot of data, and especially when it's privacy relevant data and contains personal identifiable information, you have to be very careful not violating any current or future privacy laws that might be out there. So that means you cannot leak the data. You cannot store it without having any reason. You cannot transfer it unlawfully, and so on and so forth. So it's a very complicated topic, and it's increasingly complex the more data you as a company have. And one of these big data sets that we and also other companies are dealing with are collecting data for developing automated and autonomous driving systems. So we're dealing here with very large amounts of data. So in this particular example right here, it would be images and videos from a front video camera of a car. So you can see here one of these as an example on the right-hand side. This is a car driving through an urban environment, and you can clearly see that we record person identifiable information. So we have a person looking into the camera. We have several license plates. So now there is a bunch of questions coming up. So how do we treat this kind of data with PII? How do we label it? Can we transfer it to other countries, to other companies? How free are we there to kind of share this data? How do we store it long term? How do we use it for training? And these are more and more questions, and they're all very complicated questions to answer. And in order to kind of analyze this at least a little bit, you have to, of course, first address what the most, I would say, the most popular privacy regulation or the most mature one is saying to this, and that would be the European GDPR. So the GDPR states that you need a lawful basis for processing data with PII. And then it proceeds and kind of opens the door for two different paths that you can, at least two different paths that you can take here. The first one is you can ask for consent of the data subjects. So in a lot of use cases that works. In our use cases, it's extremely unrealistic because we are driving test cars through an urban environment. We can just randomly open the door and walk around and ask everyone who could be within the vicinity of the camera if they are okay with being recorded. So this is not a realistic approach here. And fortunately, there is another way that you can take, and that would be arguing legitimate interest. So legitimate interest is something we clearly have. So we don't just record this data for the sake of having data. We are recording it because we want to use it for a specific use case. We want to develop automated or autonomous driving systems. But there is, in addition to this legitimate interest, among others, you also have to show that there is no less privacy intrusive way to achieve the same result. Or in other words, do everything you realistically can to protect the privacy of the data. And this is where it gets a little bit trickier. But being part of this conference, we thought that confidential computing would actually be a perfect way to achieve this least privacy intrusive way. So in general, when we talk about privacy-preserving computing technologies, or PPCTs as we call them, such as multi-party computation, fully homomorphic encryption, and of course also trusted execution environments, we always think that these could allow us to make this possible for the least privacy intrusive storage and processing of autonomous driving data. And if we use one of these technologies to achieve this, we have at least two great benefits. So on one hand, we are, of course, minimizing the risks for each data subject in the data set. So if there's a data leak, or if there cannot be a data leak, then we are protecting each individual data subject that could potentially be part of this data set. And then, of course, we are also reducing the legal risks for the company. So especially with regulations such as GDPR, there's pretty heavy fines if they find a violation. So you clearly want to avoid any complications with GDPR, and privacy-preserving computing technologies can absolutely help you here to make a good case that you are taking this least privacy-intrusive way. So our specific goal in this proof of concept is the training of neural networks using data that potentially contain person identifiable information. So we kind of started brainstorming about possible solutions to achieve this goal. And in this process, we came up with this 6-stage pipeline that you can see right here. I will now introduce shortly on a conceptual level how each of these stages kind of work together. And then later on, we will take a deeper dive into each of these technologies. And then at the end, we round that up with a demo to show that the system actually works in reality as well. So our pipeline here consists, as I already said, of 6 atomic steps. We have acquisition of images, transmitting them securely, de-identify images, store images, label images, and finally train a neural network. Let's go through this process step by step. So we start here with one of our vehicles that records images of a front video camera. Here in this example, we can see there is a person and at least one license plate that we can read. So we should consider this person identifiable information. That's why the car is now sending this image via an encrypted and authenticated channel in the transmission phase. So the image is being sent directly to a trusted execution environment. In our example here, that would be Intel SGX. And this protects the raw image, of course, from any unauthorized access. And furthermore, the car can also remotely attest the integrity of the enclave, so that it's talking to something, or it's sending the image to something that is correct. Within the trusted execution environment, we are now doing what we call the de-identification of the image. So we are using a neural network, a semantic segmentation neural network, to identify each pixel and give each pixel a label. Could this be person identifiable information or not? So this is basically a mask that masks all PII from the non-PII. We can use that mask to now split up the image into 2 parts. So here on the top of the image, we have the part that contains all the PII. And on the bottom part of the pipeline, we have everything else. So we call this sometimes background or non-PII part. And now the trusted execution environment can actually store this in 2 different databases. So the PII part, we encrypt first and then store in either in an encrypted database or in an encrypted form in a database. And on the other hand, on the bottom side of this pipeline, we can store this part in an unencrypted database from a privacy point of view, because we do not store any PII relevant data. And the important thing here to notice is that actually the vast majority of pixels are non-PII. So we analyzed a data set here that we have internally, and the vast majority of the pixels are actually non-PII, and a lot of images don't contain any PII to begin with. So the vast majority of data will end up in, I would call, the cheap pipeline on the bottom, and only a small amount of pixels will end up in the privacy-relevant top part of the pipeline. So when it comes to post-processing of the data, we can see the first big advantage of using this method. Because this lower part of the pipeline doesn't contain any person identifiable information, we have a lot more freedoms when it comes to storing, processing, and sharing this kind of data. So for neural networks, for example, we need labeled data, which can actually be quite expensive if you do that in-house. So we as Bosch, we are not like a dedicated labeling company, so it is usually relatively expensive for us to do. So it would be ideal to offload that into to companies that are dedicated to doing this. And because we are actually de-identified the images, we're pretty free with how we share this kind of data now, because there is no privacy-relevant parts in this image left. So ultimately, this will yield very precise and cost-efficient labels for us, which we can then, of course, also store in the unencrypted database. After we are done with the labeling, we have pretty much everything that we need to train a neural network. And this is the second part where this method starts to shine. And so just like the de-identification stage, we are also doing this in a trusted execution environment. And therefore, once again, we have access to the encrypted database, and we can pull both the PII part of the image and the non-PII part of the original image. And within the secure enclave, we can now recombine both of them into the original image. We can then do the same thing, of course, for the labels, and then have everything that we need to start training the neural network. And the huge advantage here is that we are actually using the original image for the training. So we have seen quite a few other methods from other companies and also in literature that propose doing something like blurring the PII parts of images. The problem is we're dealing here with a very safety critical use case. So autonomous driving, automated driving is very safety critical. That means you have to be aware of edge cases. So if you start blurring faces, for example, your neural network starts slowly learning that anything that looks blurred could be a face. What if there's now, for example, fog? So there's pretty fast occurring edge cases that could confuse your neural network. And out of nowhere, your neural network thinks there's faces everywhere, just to give an example. So this was an overview of the pipeline on a, I would say, relatively high level. And now we can actually have a closer look at all the technologies and the technology stack that is involved here to implement this pipeline. And with that, let me hand over to Scott to introduce to you Intel SGX and Grameen.
Thank you, Stefan. As Stefan and many of the other speakers here at OC3 have talked about, PPCTs are very important for securing data. Stefan, can you go to the next slide, please? Thank you. Because when you share your data, you share your exposure as well. Now, more than ever, we're sharing sensitive data like medical records, banking information, and other personal proprietary information, such as Bosch's ADAS data, that needs to stay encrypted no matter where it resides, from your on-prem data center to the public cloud to the edge. Common security measures typically don't protect data at rest and in transit, typically protect data at rest and in transit, as we know. But often they fall short of protecting data while it's actively being computed on in memory, possibly the most challenging and important step in a fully encrypted data lifecycle. That's why confidential computing is such a game changer. It's an emerging industry initiative focused on securing data in use. These efforts can enable encrypted data to be processed in memory without exposing it to the rest of the system. It's dramatically reducing the potential for this sensitive data to be exposed, while also providing a higher degree of control and transparency for the users. Intel is uniquely positioned to help customers ramp up confidential computing with tools like Intel's SGX, or software guard extensions. Intel SGX empowers application developers to encrypt code and data in memory. Unlike full memory encryption technologies that leave the data within the attack surface of the OS, the cloud stack, Intel SGX allows a specific application to create its own protected enclave with a direct interface to the hardware, limiting access and minimizing the overall performance impact for both the application and any other virtual machines or tenants on the servers. Only Intel SGX offers such a granular level of control and protection of the code and data. Besides protecting from other software running in the system, SGX also helps protect from hardware-based memory bus snooping and cold boot type DEM attacks by encrypting and decrypting the data as it leaves and enters the CPU. Finally, Intel SGX provides a hardware-based attestation capability that allows the attestation of a remote application enclave to verify its integrity, as well as the platform it's running on before deciding to share any data. So how do you develop for Intel SGX? Well, currently, Intel and a few other companies provide SGX SDKs in different programming languages to allow developers to build applications from scratch or refactor existing apps that create and utilize SGX Enclave to protect specific code and data during execution. Intel's SGX SDK supports C and C++, for example. But in untrusted cloud and edge deployments, there has been a strong desire to shield entire applications from the rest of the software stack and the infrastructure. Developers also want end-to-end solutions with a push-button approach. One way to do this is by utilizing a lift and shift development model, where an entire application and all its dependencies are placed inside an SGX enclave utilizing a library OS. This model also makes it easier to port existing applications to use SGX, as well as to use other programming languages with SGX, such as Python, R, etc. One such library OS that is backed by the CCC is called Grameen. This is the model and mechanism that Bosch has used to secure the ADAS application. So what is Grameen? To quote the Grameen website, Grameen is a lightweight guest OS designed to run a single Linux application with minimal host requirements. Grameen can run applications in an isolated environment with benefits comparable to running a complete OS in a virtual machine, including guest customization, ease of porting to different host OSs, and process migration. Utilizing Grameen, the entire application and all its dependencies run inside an SGX enclave, where Grameen provides a shielding layer from the rest of the untrusted OS software stack. Enabling applications in Grameen requires a manifest, defining the required application security policies to be enforced by Grameen. All security critical paths are hardened against eavesdropping and/or attacks. Grameen also supports dynamic library loading and integrity checking of the loadable libraries. Finally, with the help of the available Grameen shielded containers tool, an already existing containerized application can easily be transformed into an SGX protected application.
All right, thank you, Scott.
Thank you.
All right, so with Grameen and Intel SGX, what we have so far is essentially we can more or less lift and shift our workloads into secure SGX enclaves. And with that, we have protected our individual pipeline steps. But what we are missing here is the orchestration of our pipeline to automatically use to scale up and scale down the individual steps of the pipeline to connect those individual services. So what are the challenges that we need to solve to mesh those individual pipeline steps together? And I see the following ones as the most important ones. First of all, we need to somehow provide a form of attestation from one container to another inside our deployment, so that one pipeline step can share data with another container, and knowing that everything will stay inside secure enclaves and will be end-to-end secure. And then we need to verify and attest this whole application, our whole pipeline from the outside to third parties, to clients, to regulators and legislation. And in more technical terms, we also need to ensure that all network connections always terminate inside enclaves. And then our orchestration layer provides some means to configure and bootstrap our services where the secrets and configurational information, first of all, never leaves the enclave boundary and can be trusted, can be verified. So the configuration cannot lead to some malicious behavior of our services. And finally, we want everything to be updatable, so I can update my individual services using, for example, a rolling release model. So with Marlboro, the idea is that we add a trusted party to the Kubernetes control plane. And this trusted party is then able to bootstrap a confidential deployment and lift this individual workload protection to your entire Kubernetes deployment. So to make this a little bit more feasible, let's see how this works in practice. So as a DevOps engineer, I first of all install anything I want to install in my cluster. For example, Kubeflow. And then I install Marlboro as my trusted party inside the control plane. And I configure Marlboro by setting a manifest, which is essentially a description of how my services, my Grameen services look like, what are their hashes, how they can be verified, what configurational parameters they get, what secrets they need. All of this in a simple JSON file. And if we have done that, we did all the preparation, our cluster is ready to receive our confidential pipeline, and we can go ahead and install it. And you can do this by, like you would install any other application, in this case, for example, using Helm. So this would install the pipeline to your cluster, and then your containers start to come up, depending on your deployment model, and they will be authenticated by Maberon, will be verified, and will be provided with the configurational information and TLS credentials to establish secure connections among them. So lastly, if we now have our connected pipeline, the pipeline is ready to process your data, to move incoming video footage, images from one step to another. We finally can take a look at how a connected car would retrieve an attestation statement from Maberon that proves the confidentiality and end-to-end security of our entire pipeline, and contains a root of trust that it can then use to securely connect to any instance of our front-end service in our pipeline and provide its video stream in a secure manner, while knowing everything is end-to-end secure and the video data never leaves an enclave context. Yep, that's it from the model one side.
Okay, thanks, Scott and Moritz. I think now we have all the technology layers that we need to implement our vision of a secure and scalable AI pipeline. So let's have a look how this all can play together. So here we focus on the de-identification and the training part of the pipeline, because these are actually the parts that involve confidential computing. So firstly, we have to ingest the data that is being sent to the de-identification part of the pipeline in step number A. So we are here using KServe, that is based on Kubernetes, to do the semantic segmentation of the image. KServe offers, for example, for TensorFlow, an inference service that is basically hosting a model of a neural network. That means you can send an image directly to the inference service, and you can get the mask of what is PAI and what is non-PAI as a result. A separate port that is also mentioned by Maberon and running on SGX is taking care of receiving the image, forwarding the image to the inference service, using the result to split up the image into two parts, and finally storing the PAI part of the image in an encrypted form on the Azure Blob Storage, and the non-PAI part of the image in a non-encrypted form on the Azure Blob Storage. After doing the labeling, and this is happening offline, so we don't consider this here on this pipeline, we can go directly to step number C. So we have everything that we need for training. We have images and labels. And here we use Kubeflow as a technology. And Kubeflow allows Kubernetes-based scalable workloads of TensorFlow networks. So as an example here, we have TF job for TensorFlow that can be used, for example, to implement a scalable training of a neural network. Here we're using a three-part approach of a TensorFlow job, where we have a chief, we have a parameter server, and we have a worker. The chief pretty much coordinates the whole training process. The parameter server hosts the model, so it's basically responsible for receiving the gradients, updating the model, and forwarding the new model to the workers. And the workers are the ones that do the actual heavy lifting. So they are the ones who get the image. They actually pull the image directly from the database, run it through the network, compute a gradient doing backpropagation, and then give that resulting gradient back to the parameter server. All of these pods themselves are totally scalable. So if we need more parameter servers or more workers, we can easily scale that up and scale that down. And each one of them is running inside an SGX protected Grameen library OS that is also being controlled by Maberon. So everything is pretty much enabled to securely communicate with each other, and we can protect the confidentiality of both data and code in these pods. So everything in this pipeline, as I already said, is completely scalable. So for example, if we go back to the de-identification part of the pipeline, if we have multiple cars or a lot of thousands or millions of cars sending images to the backend, we can easily scale up the inference services so that we can process more images at the same time. On the other hand, if we have a large network that we want to train, or we have a lot of training or test data that we have to train on, we can easily scale up the parameter server and the worker within the Kubeflow. Okay, so I think I showed you guys that we were able to implement a privacy-aware inference and training of neural networks. After the slide, we will also show you guys a demo to show you that it actually works. So this is not just a vision. This is actually something that's already deployable. We are using fast, trusted execution environment technologies. So here in this example, we teamed up with Intel and used Intel SGX. We do support TensorFlow models out of the box. So this is something that we've seen is very important to a lot of customers. They don't want to rewrite their models or their data or anything like this. They usually have an established pipeline. They don't want to change anything at all. And the good thing is here we support them thanks to us using Grameen pretty much out of the box. And last but not least, everything in this architecture is completely scalable and distributed. So I think Felix said it earlier. We are moving to everything in the cloud. So this is a very important requirement for any pipeline these days. And we are happy to announce that it also works with heavy workloads inside Grameen, inside SGX, while still having everything scalable and distributed. And with that, we can have a look at the demo.
Let's imagine this situation. One of our test vehicles is driving in an urban environment. We want to record all images of the front video camera and store them in the backend. Now we get to a crossing, where we would collect data that contains personal identifiable information. In this case, a person looking directly into the camera. We can use our pipeline to find a solution to the goal of wanting to train neural networks using this kind of data. We will run through all 6 stages and show the technologies involved. Let's start with the de-identification stage that allows the car to send images securely to the enclave. We set up an Azure Kubernetes cluster using SGX-enabled nodes. Let's connect to the cluster using the Azure Cloud Shell. We can get the Kubernetes config and merge it into our local config in order to access it using kubectl. Here we can see all pods that are involved in the pipeline. We have the predictor marbles, Kserve, Kubeflow, Intel SGX, and of course, Marble Run. Now we pretend to be the car in this communication, wanting to send an image to the de-identification enclave. As we are already connected to the cluster, we only have to forward a local port in this case. Normally, we would connect to an external IP. The car is a simple Python script that sends a front video camera image from its file system to the de-identification enclave. It uses a certificate in order to establish a gRPC channel with TLS. The de-identification controller is now receiving the image, forwarding it to the inference service of Kserve, receiving the mask, and using it to split up the image. Finally, the PII part is encrypted. Then both parts of the images can be stored on an Azure Blob Storage. All of this is happening on SGX protected pods controlled by Marble Run. Once this process is done, the car gets a confirmation from the de-identification enclave. Let's have a look at the results in the blob storage by using the Azure Storage Explorer on the right-hand side. We see 2 images, one the non-PII part of the image, and the other one the PII part of the original image. We can see that the non-PII part of the image doesn't contain any personal identifiable information anymore. The person is clearly cut out, and the license plate in the background is not visible and hence doesn't need to be cut out. We can now look at the PII part of the image in the Azure Blob Store. In this example, we didn't encrypt the image so that we can have a look at it directly. The person looking directly into the camera is in the PII part of the image, as well as 2 persons in the background. There's actually some artifacts in the image, but this can be easily fixed by using an improved neural network. The car, or any other entity, is also able to verify that Marble Run is running properly. First, with the command Marble Run status, we can check that Marble Run is healthy and is able to accept marbles. We can see the response from the coordinator that everything is running correctly and Marble Run is ready to accept marbles. Now we can verify that Marble Run is using the correct manifest. The manifest is similar to the one of Kubernetes and defines the topology of the cluster, as well as the secrets and the users that can authenticate themselves against the controller. With the verify command, we can compare the remote manifest with our local manifest. In this example, the local and remote manifest are a match. If, however, we use a different local manifest, we will be informed that the signatures are different. Let's have a look at the manifest of this setup. There are different packages for the de-identification and training part, as well as all the separate marbles for the different tasks, such as parameter server, worker, and so on and so forth. Furthermore, we are defining all the secrets that are being used by Marble Run, as well as the users that are allowed to authenticate themselves against Marble Run, as well as the different roles. We can also get the manifest directly from the Marble Run controller by using the manifest get command. Finally, we can check the log file of Marble Run to verify any changes to the system. Here we can see a couple of changes to the Azure Blob Storage, where we actually changed the Blob Storage account. This process can be repeated for more images until we have enough data for the training. With the images being separated and stored in the database, we can now generate labels for our images. As this can be done offline, we only have a look at the final result. This image shows the semantic segmentation label of one of the images in the database. Now we have everything we need in order to train a neural network. The PAI parts in the encrypted database, the non-PAI parts in the unencrypted database, as well as labels for both. The training topology is defined in a YAML file, which can be applied to the cluster. This file basically contains the configuration of our Kubeflow cluster. We can adjust things like the amount of parameter servers and workers, as well as assigned resources per pod. All the pods are Marble Run aware, and therefore will be controlled by Marble Run and run in an SGX protected Grameen container. After applying the YAML file using kubectl, we can see that the chief, the parameter server, as well as the worker are being deployed on the cluster. Using the kubectl log command, we're observing the activity of the chief in the bottom left corner, of the parameter server in the top right corner, as well as the worker in the bottom right corner. After a successful setup phase, we can see that the neural network starts training, and the chief gives us the log output of the current status of the training. We can see how the epochs are progressing, and the accuracy is getting better and better. During this process, the workers are pulling the images directly from the encrypted and unencrypted database, recombine them, use them for training, and then remove them again. This ensures the end-to-end protection of the confidentiality of the images. After a few minutes, we see that we finished the training and we stored the final model on the Azure Blob Storage as well. Now we have successfully trained a neural network using data with personal identifiable information. Thanks to technologies such as Intel SGX, Grameen, Edgeless Systems Marble Run, Kubernetes, Kserve, as well as Kubeflow, we achieved a scalable, distributed, and end-to-end protected implementation.
All right, I think that rounds up the video.